Hello everybody, welcome to the seventh lecture, and we will start a new chapter, that is the field dependent electric strength and breakdown in gaseous dielectrics and also in vacuum, because vacuum becomes part of the you can say gas, or when the gas is evacuated. So we will talk about together for gaseous dielectrics and vacuum. In this course, the objectives are that we learned properties of the gaseous dielectrics and then the mechanism of the generation of charge carriers. The charge carriers actually lead to breakdown. And the basic process of breakdown is not just the ionization, because ionization exists even otherwise, without electrical field. But when electrical field is applied, the process begins. The ionization process is very systematic, and it begins in the form of an electron avalanche. That we will be talking about that electron avalanche, and then the breakdown mechanism uniform field, which is the first experiment in uniform fields being performed by Townsend, and then later we have developed how does the breakdown mechanism takes place in weakly non-uniform fields. We have already learned the weakly non-uniform field configuration, and then the extremely non-uniform fields, which is most common in the electrical network. And then we will be talking about the space charge, the picture of a space charge. Space charge also you learned what it is the concentration of like polarity charge in nothing but space charge, we call it, and it affects the performance of the dielectric. Let's begin with this new chapter. We will be talking about the practical measurements, and after the practical measurements, the fitting theories to the experimental results have been involved. We talk about that. Then the common gaseous dielectrics, the most common gaseous dielectric, as I have been mentioning, is nothing but atmospheric air. And you'll be surprised to know, if you see in high voltage engineering, the maximum work, practical and practical measurements, etc., have been performed in atmospheric air. That means with atmospheric air behaving like a dielectric. The advent of other insulating gases did come, but it was something like more than half a century ago, that SF6 gas, that is sulfur hexafluoride, an electronegative gas, was identified to be one of the most suitable, today one of the most suitable compressed gas for electrical insulation. Vacuum technology is there since long, but it has its own limitations. It has grown up. The use of vacuum technology in power system network of power system apparatus has increased, but not to the extent the SF6 gas application. As I was mentioning, there are two types of gases: the electropositive gas and electronegative gas. So, for example, nitrogen is an electron positive gas, and SF6 gas is electronegative gas. That means what happens in electropositive gas, an electron is absorbed, an electron is ejected out from the molecule in electropositive gases and leaves behind the positive ion. Whereas in electronegative gases, an electron is absorbed and gives rise to a negative ion. So, electronegative gas absorbs that free moving electrons, whereas electropositive gas like nitrogen would eject out, produce more of electrons. We'll be also talking about the mass of electron versus the mass of the ion. Mass of the electron is much lighter as compared to the ion or molecule. So the drift velocity, we call it to be, the drift velocity of electrons is much higher than that of the molecules. And for certain places, we assume as if the ions are stationary, when the electrons are moving. So that is how the movement is dependent upon the mass of the small tiny particle, of electricity. And then we have two types of collisions: elastic and inelastic collisions, when an electron meets the ion. We will be discussing that also. The air constitutes of major portion of air constitutes of nitrogen, and then the second highest composition is that of oxygen. Then nitrogen is something like 78%, oxygen is 20%, and rest of the gases in the air are very, very small percentage wise. So there are gases like argon, carbon dioxide, neon, helium, methane, krypton, hydrogen, nitrous oxide, carbon monoxide, ozone, and of course water, humidity content is also there in the air. So this is the composition of air, atmospheric air. As we learn, the nitrogen is the maximum, and second highest is the oxygen. Oxygen is an electronegative gas once again, but nitrogen is an electropositive gas. So the quality of oxygen and SF6 gas are somewhere similar, but electropositive gas, nitrogen, does not again. It dominates in the atmospheric air. So the properties are determined by the electropositive nitrogen, that of atmospheric air. So air is used as a model of electrical discharge. Why? Because it's very simple and very easy to work on atmospheric air as compared to any other gas in a controlled chamber. In case of air, you don't need to uh, make experimental work necessarily under compressed gas. Some compressed atmospheric air work has also gone through. So if you see the literature in high voltage engineering, the maximum number of applications, maximum number of work people have done is that on atmospheric air. So as compared to atmospheric air, let's talk about SF6 gas, the electronegative gas. I did mention that the intrinsic strength, that is the inherent strength, which is measured in the case of gaseous dielectrics in uniform field for a gap distance of 1 centimeter. For SF6 gas, it is 89 kV per centimeter. So you can say almost 90 kV per centimeter, whereas it is 31 kV per centimeter in case of atmospheric air. So the SF6 gas intrinsic strength is 3 times that of atmospheric air. Obviously, when we are talking here, is the strength is measured at atmospheric pressure and temperature 20 degrees centigrade and atmospheric pressure. For SF6 gas, it works out to be 89 kV per centimeter. And we can see the other properties of SF6 gas, as you can see it here in the list here. Here are the details given for the properties of the SF6 gas, and these details are quite suitable for the application of SF6 gas in power systems. Yeah, one very important thing is what happens when what we are going to investigate is how does the gas behave, or gaseous dielectrics behave when we apply voltage to the gas. I mean, see, the very obviously you would say what happens if applied voltage at electrodes increases. Obviously, some phenomenon will begin, and we are going to work on that. What happens? What kind of phenomenon begins when this happens? First is ionization. That may begin at quite a low voltage, or let's not say voltage, so it would be better to say at what electric field intensity does the ionization begin. There is always a magnitude of electric field intensity, what we call it to be I. Later we will see in capital E and capital I we have taken for in this book is the ionization, I for capital I for ionization. The process of build-up of high currents in a breakdown in which electrons and ions are created from natural atoms or molecules, and their migration to the anode and cathode respectively leads to high current. Let's not talk first about the high current buildup. initial also the ionization takes place. Ionization may take place at the electrode or within the gas. So we will analyze how does it. The next comes the ionization actually develops in the form of an avalanche. We learn what is an avalanche, an electron avalanche, which comprises of the electrons as well as when the electrons are formed because of ionization, it leaves behind the positive molecules. So the molecules and electrons together develop or grow by increasing the voltage in the form of an avalanche. That is, an avalanche contains both electrons and the ions. And when you increase the voltage further, what happens? The avalanches acquire a certain size. We put it as critical amplification of avalanche. And when critical amplification of avalanche is able to develop, we call it streamer process begins. A streamer breakdown mechanism, that means where the avalanches are formed of higher above critical amplification. The factors which affect the ionization is nothing but the physical condition of gases like temperature, pressure, electrode field configuration, nature of electrode surface, and the availability of initial conducting particles. That is, to begin the ionization process, you have to have one, you can say, some electron or ion present. When there is an electron, that means ion should be accompanied with that. So some charge particle has to be there to begin a process. So which is determined or which depends upon physical conditions of the gases and obviously on the magnitude of the light voltage. So we call it the ionization to be the primary ionization process. That is because of the impact ionization. Electrons, which I was mentioning, have got a much higher speed because they are lighter as compared to the molecules. So they move very fast, and when the impact, when they make an impact with the neutral molecule, they eject out another electron, and the ionization process cascades. You can say it's an exponential process. In an exponential process that increases the ionization. So you can say charged particles are formed by one single electron number of times when on impact with the neutral molecule. We have a photoionization, that means the photon also make ionization. That means they produce a charged particle. Electron emission due to photon takes place. Then the secondary mechanism with which the ionization takes place is electron emission due to positive ion impact. It happens that ions heavier bounce back on the electrode and release an electron. That means positive ion impact on the electrode also gives rise to electron emission, that is secondary ionization. Electron emission due to metastable and neutral atoms also takes place. Metastable are the molecules at vibratory state at higher thermal energy. Thermionic emission or thermal ionization, when the temperature of the gas is increased considerably, there is a process by which the thermionic emission, we call it thermal ionization also. Because of the heat, the ionization also takes place. And the field emission, that means because of the high electric field, the electrons may be produced in a dye. Then electron attachment would take place in electronegative gas, and the electrons are absorbed by the neutral molecules of the electronegative gas, forming negative ions, and electron diffusion recombination processes also take place. Let's apply ourselves. The generation of charge carriers in gases a little more closely. In a gas, the electrons and ions are the electric charge carriers, as I mentioned. Ions are produced from neutral molecules or atoms by ejection or attachment of an electron. The total energy of an electron can be divided into two types of energy. That is the total energy. That is the kinetic energy for the movement of the electron, and the potential energy. That means the potential energy acquired by the electrons, and the equations for kinetic energy is given half m electron v square, the speed of the electron, and the potential energy is also given, as you could say, read here, and that works out to be equal to twice as much as the kinetic energy. So the kinetic energy is smaller as compared to potential energy. So the equation for total energy in the electron is given here. That is the kinetic energy and the potential energy together, which works out to be this total energy, works out to be this one, 13.6 eV z square by m square. So m is the orbit, and this is known as the negative of ionization energy. That means this much energy is required for making an ionization. For a small gap distance between electrodes, ions can therefore be assumed not to have moved from the place where they are generated because of the difference in the potential and the kinetic energy. So they are considered to be more or less stationary. What is an electrical breakdown? What actually happens in electrical breakdown? We know that when an insulating material loses its insulating property, that a breakdown in the dielectric occurs. The breakdown in a dielectric is accomplished when you apply the voltage or increase the voltage applied. The breakdown, that is the conducting path through the dielectric, is formed, and that we call it to be a canal or a channel. And the two electrodes are bridged by this conducting path. In small gap distance, the charge carriers required in order to build this discharge canal are not only produced within the gaseous dielectrics. Across the gap, there is a primary and secondary ionization process, but also released from the electrode surface, that is the gamma process. That was the work by Townsend, and he distinguished the primary alpha process, that is when within the gas the electrons are produced, and when electrons are produced by the impact of ions on the electrode surface, secondary ionization, that is gamma process, takes place. This is true only for very small gap distances. That means the surface of the electrode plays an important role if the gap distances are very small. But if the gap distances are not that small, the total process of ionization takes place only by alpha, or the primary process, and it takes place within the dielectric. So that is a major difference between small gap distances and long gap distances. Yeah, in order to begin the ionization process, you must have at least one charge particle available to initiate the discharge process or initiate the breakdown process. So one electron, that is single, maybe it is also known as initiator electron. You need an electron initially to be present in the gap to begin the ionization process, which develops into the avalanche process and then into the streamer process. So initial electrons, emission from the cathode, or in extreme case by cosmic rays, friction, and movement or ultraviolet irradiation or photoionization is needed to produce the initial electron. You can irradiate the electrode surface with ultraviolet irradiation, and it will give rise to an electron on the surface. If it is not, it may be on the surface, we call it, but slightly not very correct. So on the surface, it will get conductor on the surface, but in the dielectric on the surface, metallic, on the metallic surface. That is the right way to think about it, that the electron would be present in the dielectric on the surface of the electrode. Yeah, impact or impact ionization, as we or also we call it to be collision ionization. That is a collision that takes place. Collision or impact, same thing. That is, because of the high velocity of an electron, it collides with the neutral molecules and ejects an electron. The impact or collision of particles amongst each other, accelerated under electrical field, leads to the formation of charge carriers from neutral gas molecules. The multiplication of charge carriers in gaseous dielectrics take place mainly by impact of electrons in gaseous dielectric. It is the multiplication of charge particles. In fact, when a breakdown takes place through the breakdown channel through any dielectric, very large amount of current has to flow. It requires a very large, only then the breakdown is accomplished. So the large amount of current means large number of charge particles. A vigorous ionization process is needed under the breakdown condition to provide the current flowing through the dielectric under breakdown condition when the dielectric has lost its insulating property. The multiplication of charge carriers in gas takes place mainly by impact of electrons and neutral molecules with neutral molecules known as alpha process. As you can see, an electron moving towards a neutral molecule and ejecting another electron. So in the orbit of the molecule electrons, the two electrons, and the energy is given with this equation, where U capital I is the voltage required for ionization. To begin with, at this voltage, the ionization process would begin. Ionization by electron impact alpha process, and in the lower, ionization by positive ion also takes place. As you can see, positive ion is made here. Positive ion makes impact with another neutral ion and ejects an electron, and that is how the energy there is more. In fact, the energy here is 2E ui, where it is only E ui in case of impact ionization. The second one is known as the beta process or secondary ionization process, and A is the primary ionization process or alpha process. To cause ionization, the incoming electron must have kinetic energy greater than or equal to the ionization energy of the molecule. I mean, the incoming electron must have sufficient energy to be able to make a successful impact and produce another charged particles, another electron, and to accomplish the ionization. So the first ionization energy W capital I, which is in electron volt, for different dielectrics are given here. For nitrogen it is 15.6, well for SF6 also 15.6 electron volts, and these are two gases, you can say, of more importance to us. Yeah, thermal ionization. This was the impact ionization we discussed. Now we would talk about the thermal ionization. What is the thermal ionization? Thermal ionization also takes place if a gas is heated to sufficiently high temperature to the order of 10,000 Kelvin and above. Many of the gas atoms or molecules acquire high velocity to cause ionization on collision with other atoms or molecules. The molecules excited by photon radiation also affect the ionization process, because when the temperature of the gas rises so much, there is light produced, photon are also there, and the molecules excited by photon radiation also affect the ionization process. Thermal ionization is the principal source of ionization in flames and arcs. Arcs are the when there is a very high short circuit current flows between two electrodes that forms at beyond a certain magnitude of the current when the conducting channel acquires very high temperature, there is arc produced there. The temperature versus the theta is given in the figure there. Degree of ionization of thermally ionized gases at 1 bar is here. The theta is the degree of ionization, and with respect to temperature for SF6 gas, nitrogen, and air are drawn in this curve. Thermal ionization becomes significant only at temperatures above 10,000 Kelvin, as I mentioned, and it can be seen in this figure. It is 10,000 Kelvin, the temperature here, 10,000 Kelvin, and here the thermal ionization begins, and the temperature may rise very high, something like 25,000 Kelvin may rise right here, and the degree of ionization then is increases, you can say, the degree of ionization increases with the increase in temperature of the gas. During electrical breakdown in gases, thermal ionization has its significance only towards the final stage of breakdown. That means that, we call it in gaseous dielectrics, the breakdown always takes place with unstable leader leading to formation of arc. Unstable leader is produced, and which takes the form of an arc when the breakdown is accomplished. And because of transformation of large amount of energy in the electrically conductive channel, that is the leader, towards the final stage of breakdown, and exceptionally high temperature is in this channel core would be produced. Photoionization. So we learned impact ionization, thermal ionization, and now the photoionization. The phenomenon associated with ionization by radiation, which involves the interaction of radiation with matter. Photoionization occurs when the amount of radiation energy absorbed by an atom or molecule exceeds as ionization potential. See, the atom gets excited because of photons also. So the excitation of the atoms to a higher energy state may also take place. If it is unable to ionize, it is lifted up to a higher energy level of the gas or of the atoms. The photons may raise the atom to a higher energy level. The impact ionization process is possible only when the energy exchange in collision is more than the energy released energy required for ionization. That is, EUI is the energy required for ionization. So unless the energy exchange in collision is more than the energy required for ionization, impact ionization will not occur. The electrons having energy lower than the ionization energy may excite the gas molecules to higher energy state or higher energy level on collision. Under this condition, an electron is raised from lower energy level to a higher energy level, and this on recovering from the excited state of electron at higher energy level in 10 to the power minus 7 to 10 to the power minus 10 seconds, a molecule radiates a quantum of energy of photon, and this energy in turn may ionize another molecule whose ionization potential energy is equal to or less than the photon energy. So this is how when at molecules at higher level of energy are there, they are also called as metastables, which I was mentioning. The electron emission to photon, the secondary photoionization, you can say the secondary photoionization, to cause an electron escape from a metal. It has been, the physicists have worked a lot, and as I was mentioning, when this would matter if the gap distance is not very large, that the cause of an electron escape from the metal, that the metal is able to eject or give rise to an electron, it should be given enough energy to overcome the surface potential barrier. The surface potential barrier of the metal, which is also known as Schottky effect, you might have learned in physics. So the metals, from the metals, the charged particles are ejected out or produced when the surface potential barrier is exceeded, that is, the Schottky effect is there. Excited molecules in the avalanche may emit photons on returning to their ground state. These excited molecules are the metastables, also known as metastables, in the avalanche may emit photons on returning to their ground state, energy level. This radiation falling on cathode may produce photo emission of electrons. So I think we can make a break here, and in the next lecture we will talk about the development of electron avalanche. Electron avalanche, as I mentioned right in the beginning of this lecture, is a very systematic growth of the electron or ionization process. This electron avalanche can be said to be a systematic growth of ionization process, which is nothing but an avalanche, in the form of an avalanche. The avalanche process exists in nature very much, and we will learn what is an electron avalanche. Scientists have devoted their lives to be able to understand the electron avalanche and how does it behave, and we will learn about avalanche, an electron avalanche, which is the first and the most significant process in any gaseous breakdown. It is, you need millions and millions of avalanches to be produced, which comprise of nothing but charged particles, to be able to accomplish the complete breakdown in the tablet. So that we will look at tomorrow, and yeah, this is this is an electron avalanche, which we will be talking about in the next lecture. Yeah, we can talk about it in the next lecture because the time is almost over. Yeah, we have talked about 15 minutes.